Welcome. In this video we are going to see how to find the derivative of inverse trigonometric functions and also how to go backwards and do the integration on the results of inverse trigonometric functions. And also we'll be dealing with some exponential and logarithmic functions which are not to the base of e, which is to the base of numbers other than e. Okay, first let's look into the inverse trigonometric functions. So the inverse trigonometric function would look like, say, the first function would be arc sine, which is sine inverse of x. For this we need to find dy dx. Okay, now arc sine is sine inverse, therefore by definition of inverse functions this is sine y is equal to x. Use the implicit function for this. Sine y becomes cos y, and you need to use dy dx here because it is with respect to x, and on this side it would be equal to 1. Therefore cos y dy dx is equal to 1, which means dy dx is equal to 1 over cos y. Now we are using the trigonometric identity, which is cos y, cos of an angle, is equal to 1 minus sine square of the angle, right? So that's what we are going to use here, which is 1 over root of 1 minus sine square y. We know that sine y is x, therefore this is 1 over root of 1 minus x square. Therefore differential of arc sine x is 1 over 1 minus x square. Okay, next, arc cos x. It's a similar one. The method is the same, where you need to write cos y equal to x and then use implicit function, but in this case it would be minus sine equal to 1, and therefore dy dx is equal to minus 1 over sine y, and use the same identity. This would give you 1 over root of 1 minus cos square y, which is x square. In this case cos y is x, therefore it's negative 1 of 1 to the 1 over root of 1 minus x square for arc cos x. Okay, next would be y equal to arc tan x. Again the same principle here, tan y equal to x. Differential of tan y is secant square y, and differential of y with respect to x is dy dx is equal to 1, and therefore dy dx is equal to 1 over secant square x. You might wonder why I'm writing 1 over secant square x. It could be cos square x, but I'm not going to change this to cos square x because I'm going to use the trigonometric identity between tan y and secant square y. So which means that tan square y, I think it is secant square y minus tan square y equal to 1. This is the identity we can use, which says that secant square y equals 1 plus tan square y. So this is 1 over 1 plus tan square y, and remember there is no square root because here it's in square, whereas in the previous cases there was no square with the sine or cos. So here it is secant square y, therefore there is no square root, therefore this is 1 over 1 plus x square. Okay, there is no square root for arc tan, remember this. Next would be to find, going backwards. Let's go backwards and see what the integral would be then. Okay, so which means if arc sine x derivative is 1 over root of 1 minus x square, then integral 1 over root of 1 minus x square should give me, with respect to dx, arc sine x as my answer on integration plus a constant c. So it's easy, right? What happens if it was integral of 1 over square root of a square minus x square dx? So here I can write this as, I can take the a square out, which would be root of a square times 1 minus x over a the whole square. So I'm taking the a square common here, so a square would be 1, and this x square, when a square is out, it's x over a the whole square, which is 1 over a outside. This a square within the root would be a, integral 1 over root of 1 minus x over a the whole square. Okay, which means This is 1 over a integral 1 over root of 1. I'm writing this again, x over a the whole square. Now we know that 1 over root of 1 minus x square is arc sine, just now we found. So 1 over a arc sine of the variable inside the bracket is x over a the whole square. If it was x square, we had sine x, but here it is x over a, therefore x over a the whole square. Therefore it is arc sine of x over a divided by 1 over a, as we have integral of composite functions with linear functions, right? If it is sine ax plus b integral with respect to dx, then it would be minus cos ax plus b divided by the derivative of ax plus b, which is a. In this case, the derivative of x over a is 1 over a, that has to be divided here, which means that this goes off and the answer is just arc sine of x over a, which was for the integral of 1 over square root of a square minus x square dx. Hope this is clear. Now let's do arc tan, or is arc cos. So we'll be finding minus 1 over square root of 1 minus x square dx. We can just write this as arc cos x, but usually we don't use this. Why? Because this is minus, and if you look at this part, which is integral 1 over root of 1 minus x square dx, was just now we saw that this is equal to arc sine x, right? So it's just with a minus sign here, so you put a minus sign here. So you don't need to write it as arc cos x, it could be arc sine x plus c, and you can always write this as arc sine x. You need to just remember that 1 over root of 1 minus x square is minus arc sine x when you have minus here, otherwise it's just plus arc sine x. Okay, similarly in the same way, if you have 1 minus a square minus x square, then dx, it would be minus arc sine of x over a, as we just did now. Now let's do inverse, that is the integral of arc tan x. So what is the answer? The answer is here. So integral of 1 over 1 plus x square dx would give you arc tan x plus c, because that's the way the integration works. It's antiderivative. But we are more concerned about finding something of this type, a square plus x square. Okay, so how do you simplify this? 1 over, I take the a square out because I want it as 1 plus something square, right? That's why I'm taking the a square out. So if I take the a square out, I'll get 1 plus, and this would be x over a the whole square. So which is of this form? 1 plus something square, and that something is x over a here. Okay, now the 1 over a square can come out of the integral, which is 1 over 1 plus x over a the whole square and dx. Now using this 1 plus something square is equal to arc tan of something, then it would be 1 over a square arc tan of x over a, and as it is, as you know, we have to divide by the differential of x over a. So divided by 1 over a, and again this gets cancelled, only one a gets cancelled, so this is arc tan of x over a divided by a plus c, or we usually write it as 1 over a arc tan of x over a plus c, which is actually the integral for 1 over a square plus x square dx. Here you should understand that you have this special thing 1 over a for a square plus x square. The ones that we did before was 1 over a square minus x square within the square root. Okay, be careful about the actual notation there. Now the next thing we would be doing is, okay, let me do 1 or 2 problems with that. What if you have arc tan of, say, 2x, simple, then dy dx would be 1 over 1 plus 2x the whole square times 2, which is 2 over 1 plus 4x square. The times 2 comes from chain rule. This part is for arc tan x and this is for 2x. This is chain rule. So we need to use chain rule if you have some other function inside the arctan function. For example, y equals arc tan of 3x plus 4. Then the answer would be 1 over 1 plus 3x plus 4 the whole square times 3. Okay, if you have y equal to arc sine of say 5x minus 1, then it is 1 over 1 this is square root of 1 minus 5x minus 1 the whole square times 5. Okay, I think this is clear here. Next, let's move on to the functions of the form y equal to say secant x. How do you find this? In this case, how do you find the derivative of secant x? Y can be written as 1 over cos x, and you can use the quotient formula for this. So which would be cos x times 0 minus 1 times sin x minus sin x, which becomes plus sin x over cos square x. Right? This is y dash, which is sin x over cos square x. I'm writing cos square x as cos x times cos x. So what happens here is sin x over cos x times 1 over cos x, which is tan x secant x is the value is the derivative of secant x. Okay, so what about cosecant x? I think you can easily do this as a trial for you, as a practice. Take it as 1 over sin x for cosecant x and use the same thing, and you will be getting minus cosecant x cot x. You can try this out by yourself. Okay, what about cot x tan x? What is the derivative of tan x? In this case, tan x should be taken as sin x over cos x, and again you need to use the quotient rule, which would be cos x and sin x is cos x minus sin x, and derivative of cos x is minus sin x, therefore plus sin x over cos square x. So this is cos square x plus sin square x is 1 over cos square x, which is secant square x. Therefore derivative of tan x is secant square x. And the same applies for cot x, where you have to take cot x as cos x over sin x. You can try this out and see what you get here. Okay, the next thing we are going to do is about the functions y equal to a power x. Whenever you have a power as a variable, it has to be taken down, and the best way to bring it down is using ln on both sides. And now you use implicit function. Ln of y is 1 over y dy dx, and x times ln a. Ln a is a constant, therefore this is ln a. When you find the derivative of x times ln a, it is ln a. Therefore dy dx is y times ln a, and y is a power x, therefore a power x ln a. So how does it apply? You can say y equal to 3 power x. Then dy dx is ln 3 times 3 to the power of x, that is, this is ln 3 times 3 power x. Okay, and this is the reason why you are getting e power x as e power x. What happens here, if you apply the same formula, the derivative would be e power x times ln e, and you know that ln e is 1, so therefore you get e power x as the derivative of e power x. Okay, next, y equals log x to the base of a, some other number a, not e. So you can change this and write it in the form a power y equal to x, and then you can use implicit function a power y log a ln a, sorry, times dy dx equals 1, right? A power y is a power y ln a, and that's what we just saw. A power x is a power x ln a is what we saw, but since it's y, we need to make a dy dx here. Okay, that's what I did here. Therefore dy dx is 1 over ln a times a to the power of y. Now what is a to the power of y from here? A to the power of y is equal to x. Therefore 1 over x and ln a.